Okay, thank you for kind introduction. My name is Taeyeon Park from Ewha Women's University, Seoul, Korea. Today I'm going to talk about some linker for the biosensors, especially for the immobilization of this protein on the carbon-based sensor material. As you know, the biosensor consists of mainly two parts, biomolecule and transducer. And we often need a linker to combine these two parts. So in this talk, I'm going to talk about this receptor protein as a biomolecule and carbon-based material, nanomaterials such as carbon nanotube and graphene as a transducer nanomaterial. So this is one example. So in this case, we use the olfactory receptor. This is olfactory receptor, and this is carbon nanotube material as a transducer nanomaterial. So you can see this is a olfactory receptor, and this black rod represent the carbon nanotube. In this example, the olfactory receptor surrounded by lipid membrane was just adsorbed on the graphene surface. This is one example. And another example, in this case, we also use the olfactory receptor as a biomolecule. And in this case, we use the graphene as a nanomaterial for the transducer. So this olfactory receptor was immobilized on the graphene material using this linker. This linker consists of two parts. This part as a ring structure binds with graphene by pi-pi interaction, and another end, this is aldehyde group, reacts with the amine group of receptor protein. So this is another example of the biolinker. And at this time, I'd like to go into briefly about the olfactory receptor as a biomolecule for the biosensor. The olfactory receptor is a 7-transmembrane protein. It is a membrane protein. It crosses the membrane in and out 7 times. So it has very complicated structure. And it should have a genuine structure even on the biosensor, as in the cell membrane itself. And we need the mass production and high stability for the sensor material, for the practical sensor. So in order to require all these, in order to meet all these requirements, we can use receptor embedded nanodisk technique. So this olfactory receptor protein can be produced in E. coli system, that is a bacterial system for the mass production, but unfortunately it is expressed in inclusion body form, that is aggregated form. So we need to denature it first by using the detergent like this. Then we need to make a reconstitution using this nanodisk technique. Because this is a membrane protein, we need to provide a membrane environment using this nanodisk technique. So this slide shows the reconstitution steps of this olfactory receptor using nanodisk. As I said, this olfactory receptor is a membrane protein. If it is expressed in E. coli system, it is the aggregated form, so it should be denatured first completely like this. Then we add a lipid component to provide a membrane environment. Then it will make a self-assembly like this. Then finally, we use the membrane scaffold protein. This membrane scaffold protein will wrap the edge of this lipid bilayer membrane. Then we can obtain this receptor-embedded nanodisk. So this is the FESEM image of nanodisk. You can see we could obtain very uniform size of the nanodisk. The average diameter is about 10 nanometer of this nanodisk. And this slide shows a size distribution of olfactory receptor nanodisk. You can see it's about 10 nanometer in diameter. Then it should be immobilized on the sensor platform. This is one example. We use a carbon nanotube field effect transistor with floating gold electrode. So this black rods represent a carbon nanotube. And on this sensor platform, we are going to immobilize this olfactory receptor nanodisk. We can obtain the correct orientation using this HEF antibody. We use the HEF antibody. The reason why we use the HEF size of antibody is we need to decrease the distance between this biomolecule and this sensor platform to increase the sensitivity. Then this antibody specifically binds with the V5 epitope. It is expressed at the C-terminal ends of the receptor. Then this antibody binds with this gold floating electrode by this sulfide bond. Then finally, this nanodisk will be immobilized on the sensor platform with a correct orientation. So I'm going to show a short movie for this nanodisk-based bioelectronic. As I said, for the mass production, this receptor protein is expressed in E-coli system, but it is aggregated form, so it should be directional completely like this. Then we add the liquid glucose to provide the membrane environment, and then make self-assembly and use the lipid membrane scaffold to wrap the edge of this lipid bilayer, the membrane portion. This is a carbon nanotube independent transistor. Then this nanodisk is immobilized on the sensor platform, and if there is an electrical current flow along the carbon nanotube, then we can obtain the stable baseline current here. If this olfactory receptor, the odor molecule binds with the receptor, this binding will make a conformational change and also surface charge change and even cause the electrical current flow change. So by measuring the electrical current flow change, we can detect the smell molecule. This is the mechanism of this biosensor. And this is another example for the correct orientation. In this case, we use the nickel decorated reduced graphene oxide as a sensor material. And this nickel will specifically binds with the HISTAG. It is located at the end of the C-terminal ends of this receptor protein. And recently, we developed a neuromorphic olfactory system. It consists of this olfactory sensor device, and another part is synaptic device. It consists of pre-synapse and post-synapse. So this is sensing part. This olfactory receptor nanodisk was combined with graphene using this linker, the PAC linker, as kind of conventional linker. This ring part binds with the graphene by pi-pi interaction, and NHS activate the peptide bond with the receptor protein. But we can make a correct orientation, the oriented immobilization, even with our linker, if we use the amino acid tag with ring structures, because this graphene surface has ring structure and carbon nanotube surface also has ring structure, it will make a pi-pi interaction. As you know, there are 4 types of amino acid with ring structures. They are tryptophan, phenylalanine, tyrosine, and histidine. So we made this amino acid tag with ring structure to immobilize the receptor nanodisk on the graphene surface. So in order to evaluate the binding affinity, we use different amino acid tag. This is 3 sequential amino acid, 3 phenylalanine, 3 histidine, 3 tryptophan, and 3 tyrosine. So in order to detect this binding affinity, we use this fluorescence tag, FITC. Then this fluorescent intensity on graphene shows the binding affinity. This is the example of 3x histidine, 3x phenylalanine, 3x tyrosine, 3x tryptophan. You can see the 3x tryptophan show the highest maximum intensity. That means the highest binding affinity. Then we try to observe the effect of amino acid tag length on the binding intensity, the length. In this case, of course, we use the tryptophan tag, the 3x tryptophan, 6x tryptophan, and 9x tryptophan. We measure the absorbance using this ELISA method. So you can see the 9x tryptophan shows the highest binding intensity. So in this case, not only the binding affinity, but also the receptor protein production efficiency we measure according to the tag length. So we use the 3x, 9x, 6x, 9x, 12x, 15x. So you can see the 9x shows the maximum highest efficiency. So not only for the binding affinity, but also for the protein expression viewpoint, the 9x tryptophan shows the best amino acid tag. So in conclusion, so in situ amino acid tag was developed for the efficiently mobilizing biomaterials on carbon-based nanomaterials, even without using any additional linkers. And tryptophan tag shows the highest binding affinity to graphene among 4 types of ring-structured amino acid. And 9x tryptophan shows the highest binding affinity and also highest receptor production efficiency to the graphene. Okay, that's it. Thank you for attention.